Okay, this is going to be a lecture over Chapter 19, Section 1. We're going to begin the discussion of things like a current and resistance and DC circuits. So one of the first things that you're going to have to learn is the concept of current. This is going to represent the amount of charge that flows through a conductor per unit time. The SI unit is going to be the ampere, and it's going to be 1 coulomb per second. So you can see the description of it there. So if you've got a net charge that flows through a wire at a time delta t, then the current through the wire is going to be the change in the charge over the change in the time. And the way this is going to be described is the current is going to be what would be represented as a flow of positive charge. Now we all know that the electrons are actually the things that are moving, but our convention is going to be the motion of positive charge in a conductor. So I know that's going to be kind of a counterintuitive, but that's how it's going to be represented. So in the past couple of chapters, we focused on electrostatics. And there is no electric field in the interior of the conducting material. Otherwise, the mobile charges would move and the situation would not be electrostatic. In this chapter, that's going to change. We're going to have non-zero electric fields inside the conductors. So a current, or also referred to as an electric current, is going to be any motion of charge from one region of a conductor to another. So to maintain the steady flow, we're going to maintain a steady force on those mobile charges, either with an electrostatic field or by other means. So now let's assume that there's an electric field within the conductor, so a particle with charge Q is acted on by this force. You may remember that definition from before. So to help visualize current, we're going to think of conductors in the shape of wires, and we've already gone over the definition of current, changing Q over the change in time, and you're going to see the positive charges moving within an electric field. Again, it's going to be 1 coulomb per second. That is going to be 1 ampere. Currents in radio and television circuits are usually around milliamperes or microamperes. And in computer circuits, it's nanoamperes or picoamperes. In other words, very, very small amount there, but that's all you really need. An ordinary D cell flashlight bulb requires about a half to 1 ampere, and the current in the starter motor of a car engine is about 200 amps. So in this figure, the moving charges are positive and the current flows in the same direction. In this second figure down here, you're going to see that those charges are negative and they move in the opposite direction. However, we're still going to consider current as going to be from left to right, because in both cases, the result is a net transfer of positive charge from the left to the right. Positive particles flowing out at an end of the cylindrical section are continually replaced by particles flowing in the opposite end. So what you lose here is what you gain over here. So when there's a steady current or a complete circuit, the total charge in every segment of the conductor is constant. From conservation of charge, the rate of flow of charge out at one end of a segment at any instant is going to be equal to the rate of flow in at the other side. And the current at any instant is going to be the same at all cross sections. And it's not like some sort of fluid that'll squirt out of a positive terminal and then is consumed or used up. You can think of it as an excellent example of recycling to some extent. We're going to describe in circuit analysis currents as though they consist entirely of positive charge flow, even in cases where we know the actual current is due to negatively charged electrons. In metals, the moving charges are always negative electrons, but in an ionic solution, both types of ions are moving. Conventional current is going to be used to describe a flow of positive charge that is equivalent to the actual flow of charge of either sign. Think of it as sort of a net result in a sense. In a metal, you're going to have electrons that have a lot of random motion, something like this, kind of like what you see in a gas. Now, when you apply an electric field, the force that exerts on the electrons lead to a small net motion or drift in the direction of the force, in addition to the random motion. So the motion consists of not only random motion with very large speeds, but also a much lower drift speed in the direction of the electric field. Now, when you turn on the light switch, the light comes on instantly because the electric fields in the conductors travel with the speed approaching the speed of light. So you can kind of see here the path of the electron without the electric field is in blue, and then with the electric field is in pink. But with that electric field produces a net displacement along the wire. And you can kind of see what's the electric field as it's being applied here in this case. And remember, since this is an electron, it's going to go against that particular field. So anyway, you got some examples here to work. I will leave you to do that.